which will help us answer the questions at the end of the seminar and during the question and answer session. So let me get started and hand off the word to Patrick about the plans for 04.
Thanks, Alessio. Good morning, everybody. So I'd like to be, next slide, please. So I'd like to begin by giving you a brief update on the LIGO Virgo KAGRA observing runs and our current plans. The image you see on the right-hand side of this slide is from the 16th of March. It shows on the horizontal axis the years stretching from now through the end of 2028, and shows two sets of observing runs, the observing run 4 and observing run 5. The current plan for observing run 4 is that it will start on the 15th of December 2022. It will last for 1 year with a 1-month mid-run commissioning break. We anticipate doing engineering running before the start of the run in order to commission and ensure that we're at stable operations and adequate sensitivity. And during that period, we may release alerts that are not considered full-on observing alerts, but are part of the engineering period if we detect significant events. The other item that I want to mention this morning is that we may extend the 04 run if scheduling for 05 upgrades makes that viable, but you'll see in a moment how we plan to discuss that. One of the important features of the current diagram is to extend it into future runs. And the one thing to bear in mind with this is that the 05 schedule on this diagram is tentative at the present time. It is based on estimates of the upgrades and the time for the upgrades that are needed between the end of 04 and the start of 05 for each of the detectors. So we will again take a closer look at that as we go through 04 and approach the end of 04 so that we know what's going to happen for 05. The other thing that's going on at the moment is development of post-05 upgrade plans to improve the sensitivity and stability of the instruments that we have for observations that would continue past the end of this decade. They're in a tentative state at the moment, and we will begin to have some discussions of those in the future. And of course, the one thing to always mention is that continued observations are subject to funding, but from our perspective, we plan to move ahead with those. Next slide, please. The other thing that I want to mention this morning is how we want to approach discussions related to running and observing runs for the LIGO Virgo KAGRA network going forward. The first thing you should be aware of already is that we have been giving quarterly updates on observing run plans as we get ready for 04. One of the things that you've noted in those updates is that we've told you about the delays that have arisen from the pandemic due to interruptions in staff being able to get to the observatories and other laboratories, interruptions in the supply chain and other delays of those kinds. And in particular for 04, that means that we're actually starting about a year later than we thought we would be before the pandemic hit. Going forward, we're going to restart the what were called open LVEM meetings in preparation for 04. They'll be LVK really. I put K in brackets only because the mailing list and the setup is currently named open LVEM. The webinar today is targeted to provide an update on the detector upgrades that we've done for 04 across LIGO, Virgo, and KAGRA. But what we will do going into May, June is to begin to have some virtual town hall meetings. There'll be 1-hour sessions, 4 to 6 meetings between now and the start of 04. Those meetings will focus in on the technical information about alert distribution, gathering input and feedback and sharing information among everyone who's interested about plans to follow up on alerts. And then during those meetings, we'll also begin to have some discussions related to run duration to the extent that there's any flexibility. Going forward, we have some other topics that we also want to address. The first is that we are aware that LIGO Virgo KAGRA operate as within the framework of multi-messenger astronomy. And there are many missions and projects that are gearing up in order to allow us to have full suite of multi-messenger observations. So we do want to figure out a way to establish a common location for information sharing about what projects are active and proposed and timetables. We hope to also adopt or establish a workshop related to coordination of active and proposed MMA projects. And we also will want to discuss the trade-offs in 05 and post-05 plans. So with that, I'll hand over to our next speaker. Alessio, back to you.
Thank you so much, Patrick. And we move on to the next slides, and that's on LIGO. So I will call to Anna Maria.
Hi, my name is Anna Maria Fleur, and I'm a scientist at LIGO Livingston Observatory. So I'll tell you about the LIGO specific upgrades for 04. Now, LIGO operates 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana. But the upgrades are identical for both sites, even though they may be done out of order. Next slide, please. So as a summary of the improvement goals, first of all, we want to increase the circulating arm power in the interferometer by a factor of 2. And so that would, in theory, increase our sensitivity by a factor of √2. We want to increase the squeeze light efficacy to 4.5 dB from 2 to 3 dB in 03. Both of these would address higher frequency noise. And then for lower frequency noise, we need to implement this 300-meter filter cavity for frequency dependent squeezing. So in 03, we did frequency independent squeezing. So for that, I'll point you to this drawing on the right-hand side of the slide. So you can see kind of the semblance of an interferometer. The laser is coming in from the left, goes down the X arm and down the Y arm 4 kilometers to the end station, comes back, and towards us is the output of the interferometer. And so we've added this entire other skinny looking tube that is 300 meters long, 2 new vacuum chambers, an entire new vacuum tube enclosure, and an end station in order to make this 300-meter filter cavity happen. And in addition, we also need to reduce the low frequency technical noise. And we'll go into details later. So next slide, please. So what does this look like in terms of sensitivity if we want to look at the strain spectral density as a function of frequency, right? At what frequency are we going to improve? So this compares the Livingston 03 spectrum in blue with maybe some of the best we can imagine spectrum in orange for 04. So at high frequency, you can see that by doubling the laser power and somehow making more squeezing happen, we can reduce that. But the problem is, let's talk about quantum noise for a second. So at high frequency, we're dominated by the shot noise component of the quantum noise, which is kind of a phase noise. And then at low frequency, we're dominated by radiation pressure, which is sort of amplitude noise. And so when we do squeezing, we basically have the option to reduce the error in the measurement of phase noise at the detriment of amplitude noise, or vice versa. And so what we've done in 03 is we've reduced the high frequency noise, the phase noise, but we've increased a little bit the resulting quantum noise at low frequency. And so we were starting to see a bit of that in 03 with only 3 dB of squeezing. So we actually cannot do more squeezing without addressing this. And the only way to address that is to have a filter cavity that helps you kind of at each frequency rotate the amount of squeezing you apply to either the phase or amplitude error rate. Which one do you improve? Do you improve more the shot noise or more the radiation pressure? And so the resulting filter cavity that we need for the LIGO parameters is 300 meters, and that's the reason for it. And of course, at low frequency, we also have a lot of technical noises, and so you don't win that much from the filter cavity if you don't also reduce the technical noise. Next slide, please. So let's go through the topics I had in the first slide. How do we reduce quantum noise, right? So first, we want to double the arm power to 400 kilowatts. Well, we need a bigger laser. Now, making higher power lasers is kind of an established technology, so it's lower risk, but it still required a complete rebuild of our laser system. And this picture on the left here is from Hanford, where they've already done this upgrade. This is only kind of half of our laser system pictured here. So that takes time, and there are still challenges, but they've shown it can be done. So that's great. And then the bigger problem is we have these little point absorbers on the test masses, which when the laser beam lands on them, they heat up locally. And they're so small, you can see them in this little microscope picture here. And so what they do is they effectively cause losses in the arm, such that the arm power increase, it doesn't actually give you more sensitivity. So that has limited us in the past for going to higher arm power. Now we are working with a vendor to eliminate them. And it will require 1 input test mass change at Hanford. They've already done this. And it will require 2 test mass changes at Livingston. I'm going to use test mass and mirror interchangeably, so I hope that's clear. Next slide, please. Okay, so the other part of the quantum noise, we want to do more squeezing and frequency dependent, right? So the addition of this 300-meter cavity. So on the left here, you can see a photo during the construction of the Livingston beam tube enclosure. You can see a little human there with a red hat for scale, and the skeleton of the beam tube enclosure, and it's starting to be covered. You can see that white paneling. Now that's one aspect of it. So we need a frequency, we need a filter cavity in order to also squeeze at low frequency. But in order to get more squeezing, we need to have lower losses in the system. And there are kind of 2 aspects of that. Superficially, one is, of course, you want all your surfaces to have no losses. So for that, we have installed better Faraday isolators. So the picture in the middle is a picture of the output Faraday of the interferometer, newly installed at both Hanford and Livingston. And we have also implemented active mode matching. So if we're not well mode matched from the squeezer to the interferometer, from the interferometer to the output mode cleaner, which filters the gravitational wave signal, then we can risk losing 10–15% here and there. So we've implemented active mode matching, which means through different methods, either thermal or piezo, we actually can change the curvatures of the mirrors in the system inside the vacuum system. So this one of these active mode matching suspensions is shown on the right. It's a double suspension. You can kind of see the blades at the top and a little pinkish surface down there. That's the actual mirror. Next slide, please. So then we also need to reduce the low frequency technical noise, right? Otherwise, we don't win that much from the filter cavity. There's a few different aspects to this, and it's kind of a headache that we all have to deal with. So we can, some of the things that we are addressing are scattered light, controls noise reduction. We can also do subtraction, installation of better electronics where we find that they are limiting our sensitivity. Now for scattered light, we have installed a lot more baffles. So if we think of scattered light, there's kind of two components that can be attacked, right? Light escapes the system because no optic is perfect. So it just bounces off the surfaces around, picks up the motion of those surfaces, comes back, a small fraction comes back, and reinterferes with the main beam, right? So you can either reduce that light, so we install baffles everywhere, or you can also reduce the motion of the scattering surfaces. And so we've done some of that by damping some of the high Q resonances of mechanical surfaces that were scattering light into our system. And the picture here shows one of the output chambers of LIGO with human for scale, and it also shows where the new squeezer beam is going to be injected. Next slide, please. The next item I wanted to talk about is duty cycle improvement. So we are also always thinking about the duty cycle. It's quite difficult to get above 85% duty cycle per instrument. So that's kind of our goal, I think. In O3B, the duty cycle is about 75%, which resulted in a 50% triple coverage with LIGO and Virgo. Now, one of the bigger things to blame here have been high Q resonances of suspension. So we are addressing those by installing passive dampers inside the system. So for example, we are addressing the beam splitter bounce and roll modes. Those you can see are already installed on the right. They're about this big. And in the future, we plan to address the violin modes, which are the modes of the actual fibers that hang the test mass. And they're at about 500 Hertz. And so we plan to address them with the addition of this tuning mass. So we put this mass that we tune very perfectly to the vibration of that particular mass, and we attach it to the mass above the mirror. So the mass that's suspended. Next slide, please. So how do all these things fit on a schedule? This is the entire ear. So at the top in kind of reddish is Hanford, and at the bottom in bluish is Livingston. You can see we're kind of doing the same things, but a little bit out of order. If we go to the orange, let's say dark yellow, you can see that because we've had to completely disassemble our old squeezer system, put it in a new chamber, and recommission it, that's kind of what's been going on. So frequency independent squeezing, alignment, and commissioning. So we have to get that working before we're ready to include this totally new filter cavity. Hopefully by then the filter cavity and all the construction that's still going on will be done. Hanford has already done their laser upgrade and their test mass swap. We still have to do that. So we've linked those together to kind of minimize the downtime. And then there are these little blue periods where we have time to commission the flow interferometer to see the actual effect of all these installations on the low noise curve that's available at that time. So we have a few periods here and there. And then in this pre-04 commissioning, Alessia, I don't think all my slide is showing. Anyway, in this pre-04, can you go back? Sorry. In this pre-04 commissioning period, I'm kind of lumping in all the stuff that sometimes happens in engineering runs, if you know what that is. So including low latency alerts and data quality and so on. Okay, next slide, my last slide. So this is a different way to look at the sensitivity that we expect from 04 comparing to 03 and looking forward to 05, which is part of why we are implementing some of the A+ upgrades for 04, even though they were initially meant for 05. And you can see through the fatness of the gray curve, which is the 04, that's kind of our uncertainty. And I would say our biggest uncertainties are our mirrors, our technical noise reduction, and how well we mitigate the losses in the whole system. And that's all I have. Thank you.
Thank you so much, Anna Maria. Let's move on to Virgo, but before doing that, let me remind everyone, I see that somebody still is already using that there is a question and answer capability online by just pressing a small button in your Zoom window with question and answers. And with this, I leave the word to Matteo.
Yes, thank you, Alessio. So good morning, good afternoon, good evening. I will go through the upgrades that we are doing in Virgo 404. So next slide, please. Here you can see just a schematic view of the experiment with the list of the main upgrades that we are installing, starting from the input of the experiment. Also in Virgo, we would like to increase the circulating laser power. So we have to change the high power laser with a new one that will allow to send higher power into the interferometer. Then still at the input side of the experiment, we needed to install a new payload for the input multilinear cavity to improve the controllability and then stability of this cavity. And together with that, we profited to install also an instrumental baffle that has some photodiode installed on it in order to directly measure the amount of scattered light inside this cavity. Then moving towards the interferometer, there is the most challenging, I would say, upgrade, that is the installation of the signal recycling mirror towards the output of the experiment that will allow us to change the shape of the sensitivity curve. And together with that, we had to install an auxiliary system for auxiliary laser that will allow us to control all the cavities. Then at the output of the interferometer, we installed the new output multilinear cavity that will help us in reducing the losses, and also low noise photodiode in order to reduce the impact of electronic noise. As in LIGO, we are planning to install also the frequency dependent squeezing system. That means the installation of a new cavity parallel to one of the arm of the interferometer together with the squeezing source. Finally, in the experimental building of Virgo, we installed also an array of seismometer in order to be able to measure the level of Newtonian noise. And in a second step, we will try to reduce and to cancel this Newtonian noise that we're going to measure. So next slide, please. Here is a view of the sensitivity curve that Virgo reached during Go3 in the blue curve. This is compared with the band in light blue. That is the target sensitivity that we would like to achieve for 4. And starting from the high frequency bandwidth, so we would like the improvement is connected mainly to the installation of the signal recycling mirror. That is, as I said before, it is allowing us to change the shape of the sensitivity curve. And together with the increase of the input power and a higher level of frequency of squeezing, this time we will try to inject frequency dependent squeezing. Then if we go to look at mid-range frequencies, so about 100, 300, 400 hertz, here you can see that the shape of the sensitivity is changing, and it is mainly due to the installation of the signal recycling mirror. And finally, at low frequency, also we will go to handle technical noises in order to try to reduce their impact. And also we would like to profit of the frequency dependent squeezing, so in order to reduce the impact of the radiation pressure. So next slide, please. I'm going through the main upgrades that we implemented in Virgo. In particular, the first one was the installation of the signal recycling mirror together with the auxiliary laser system. So the goal for 4 is to implement the signal recycling cavity that will allow, as I said before, to change the shape of the sensitivity. And let me say that make this new cavity working properly is the most challenging upgrade that we are facing right now. So we had to install a new complete payload. So when I say payload, I mean the system that is made by the mirror, the marionette that will allow us to control the position and the angular tilt of the mirror itself, the thermal actuator, the baffle around the payload. And introducing this new cavity, we will have another degrees of freedom that we have to control. So in order to have all the knob to control of the degrees of freedom, we needed to install an auxiliary laser system that is made of green light that is sent from the end station to the central area of the interferometer. So on the bottom left, you can see a picture of the new installed payload. In the mid picture, you can see one thermal actuator that is installed on this payload and the green light that is produced to control the cavity. Next slide, please. As I said before, we would like also to increase the amount of circulating power inside the interferometer. In order to do that, so we would like to achieve a level of about 200 kilowatt of circulating power. In order to do that, we need higher power at the input of the interferometer. So we needed to install a new monolithic fiber laser that will allow us to deliver a maximum of about 75 watt injected into the interferometer. Let me say that we decided to keep the former multi-stage laser amplification on the bench in parallel to the new one, in order to have already a spare system when needed that is ready to be used. On the picture, you can see the two systems, one close to the other. Next slide, please. At the output of the interferometer, we installed also we installed new upgrades. In particular, the goal for 4 is to reduce the losses at the output of the experiment by about a factor of 2, and to improve the filtering of spurious field by 1 order of magnitude. And moreover, we would like to mitigate the impact of the scattered light. In order to do that, at first we needed to install a new output mode cleaner cavity. In the past, we had 2 low finesse cavities, one in series to the other, while now we have 1 high finesse output cleaner cavity. You can see a picture of it on the left. And not only at the output of the interferometer, but I would say more or less everywhere on the optical benches of the experiment, we installed new baffles, new beam dumps, new absorbing glass in order to absorb and to cut spurious and ghost beams that should be around and should be the source of scattered light. There are a couple of pictures as an example in the 2 other pictures of this slide. So next slide, please. The other huge upgrade is the installation of the frequency-dependent squeezing system. The goal is to reduce the impact of the shock noise at the high frequency without spoiling the low frequency, so reducing at that point also the impact of the radiation pressure noise. This means that we have to install a frequency-independent squeezing source, and we have to inject the squeezing beam before into a filter cavity and then into the interferometer. Here there is a sketch of the implementation of this system in Virgo, and there are also pictures of the different components. As in LIGO, we needed to change a bit the infrastructure, but we were lucky and we have enough room to install the vacuum pipe of this cavity in parallel to one of the arm of the interferometer. So the infrastructure work in Virgo were lighter than in LIGO. On the other picture, you can see that the suspended mirrors, the optical benches that are used for this new system. Next slide, please. So, to summarize the current status of Virgo, all the major upgrades have been successfully installed. We are now working on the interferometer with the power injected that is about 33 watt, meaning that we have circulating power in the cavities that is about 140 kilowatt. I can say that the full interferometer is now controlled, so also with the new signal recycling cavity, but it is not in an optimal working point. And this configuration, in any case, is giving us a lot of indication about the current limitation. So we are now working on the optimization of the working point. In parallel, we were able to install and to commission the frequency-dependent squeezing, and we succeeded in achieve frequency-dependent squeezing at about 40 Hertz. That is our target, and now we have to work to optimize this system. So next slide, please. So what are the next steps? As I said, for the interferometer, the first next step is to improve the current working point. That means that we have to improve the mode matching, improve the global alignment, reduce the control noise, tune the thermal state. So we have really to work on the working point of the experiment. And then we will try, and then we will start to produce a repeatable estimation of the sensitivity curve. In parallel, we are working on the optimization of the frequency-dependent squeezing, since we need to improve its stability before injecting into the interferometer. I would say that in 1 month and a half from now, we will also start the campaign of noise hunting in order to find the sources of the noise that are limiting the experiment in order to reduce them, to improve the sensitivity. And also we will start soon the preparation of the injection of the frequency-dependent squeezing into the interferometer. As you can see in this graph, we will work for the next couple of months on the optimization of the working point, but together with that, we will start also the noise hunting activities and the frequency-dependent squeezing injections, since also this can give us some indication on how to improve the experiment. And this is all for Virgo. So please, Alessio, thank you.
Thank you to you, Matteo, and we can move to KAGRA, Yoichi.
Okay, hello everyone. So I'm going to talk about the status of KAGRA for O4. So next slide, please. So KAGRA is a 3 kilometer long interferometric gravitational wave detector being constructed in Kamioka in Japan. It has two unique and sort of challenging features, which are underground site and also cryogenic mirrors for the reduction of the thermal noise. The project was started about 12 years ago, and we performed the initial joint observation in 2020 with GEO 600, which is called O3GK. The best binary range at that time was about 1 megaparsec, which means we need to do a serious work in order to get to a reasonable sensitivity to be able to actually detect the gravitational waves. Next slide, please. So in order to know what is necessary to improve the sensitivity, let me start from the noise curve of the KAGRA at that time. So the orange curve shows the measured noise of KAGRA during O3GK, and the various colored curves show the contributions from various noise sources. So let me start from low frequency. Next slide, please. So up to 100 Hertz, mainly the noises of the KAGRA was limited by so-called local damping control noise, And what does it mean by the damping control noise? Next slide, please. So it is a noise from the control. So the mirror of the interferometer are suspended by a multiple stage pendulum for vibration isolation, but these pendula have a lot of mechanical resonances at low frequencies. So at low frequencies, the mirrors will move a lot without any feedback control. So ideally, we can use the interferometer signal for the feedback control of the mirror to stop the low frequency motion. However, there are degrees of freedom which cannot be sensed well by the interferometer. Next slide, please. So we need to add a local sensor to each suspension for the damping these degrees of freedom. Unfortunately, these local sensors tend to be much noisier than the interferometric sensor. So while at low frequency, they are effective in reducing the large motion at low frequency, but in the observation band, the higher frequencies, this local sensor can introduce extra noise. Next slide, please. That is the reason for this low frequency noise. So next slide, please. So what we're going to do, this is a schematic of KAGRA, and as you can see, we have a lot of mirrors. Next, please. So after O3GK, we've been upgrading most of the suspension systems for the mirrors. So next, please. So more concretely, what we are doing is, first of all, we have several mechanical components in the suspension system which are not working well or broken. So obviously, we had to fix these mechanical failures. And after that, we have been improving various local sensors like accelerometers, ABDTs, optical levers, and so on. And also, we are improving the balance of the actuators between the suspension stages. And all of them combined allows us to better optimize the damping control filters for the suspensions so that they will not introduce extra noise at low frequencies. So this is one important upgrade for KAGRA. Next, please. In the middle sensitivity frequency range, like hundreds of hertz, we are limited by the acoustic noise coupling. While we haven't fully understood the coupling mechanism of the acoustic noise, next please, the most likely culprit for this noise is the scatter light scattered off of the main mirror and hitting the vacuum chamber wall and come back to the interferometer. Now, when this vacuum chamber wall moves by acoustic vibration, this scatter light gets extra phase noise, and that's going to translate into the extra noise in the output of the interferometer. So to stop this kind of scatter light from coming back to the interferometer, we have prepared additional optical baffles, and we're now installing these baffles. Next, please. Also, so finally, at high frequencies, we are limited by the shot noise and the laser noises, which are related to the laser power and the stability. Next, please. So the natural place to improve this noise is, of course, replacing the laser. Next, please. So we're planning to replace our high power laser from 40-watt one to the 60-watt one. Now, note that although we have 40-watt laser, during the O3GK, we were able to only use up to 5 watt because we found that this laser's intensity noise increases a lot above that power level. However, with this new 60-watt laser, we confirmed that with almost full power output, the intensity noise is actually lower. So we can use a lot more power during O4. Next, please. And we are also improving the output mode cleaner. Next, please. So the problem with our current OMC is that the transmissivity was kind of low, like only 80%. So we replaced the mirrors, and now the transmissivity is about 95%. Also, so we have 2 DC photodiodes on the output mode cleaner, which are used to do the finally detecting the gravitational wave signal. So these are the most important photodiodes. However, during O3GK, unfortunately, one of the PD was broken. So by fixing one, we can effectively double the gravitational wave signal, which is good. And next, please. And finally, we have the signal recycle mirror here, which is used to shape the optimize the shape of the quantum noise to have better sensitivity. However, during O3GK, next please, we operated in the interferometer with maybe one slide back. Yeah, thank you. We operated the interferometer with signal recycling mirror tilted because locking the signal recycling cavity requires a lot of tricky tuning of the control system, and we didn't have enough time to do so. However, the problem is that the SRM has 70% reflectivity. So this means 70% of the gravitational wave signal was just thrown away at the mirror, which is not good. So next, please. For O4, we installed extra gate valves so that we can isolate the vacuum chamber for the SRM, and we're planning to replace the SRM with a transparent one so that we will not throw away 70% of the light. Next, please. So also we're doing the upgrades on the vacuum and the cryogenic systems. So the problem with the O3GK vacuum system was that we didn't have enough number of pumps. And because of that, the vacuum level was not so great. And that means a lot of residual gas molecules are flying around. And when you have a lot of molecules flying around and still if you cool down the mirror, then these molecules will stick on the cryogenic surface of the mirror and accumulate the molecular layer, which means the kind of frost develops. And that was the reason we couldn't cool down the mirrors for O3GK. But now we have installed a lot more pumps to achieve a better vacuum. Also, just in case the frost still develops, we install the heaters for quickly removing the frost. So we're hoping that we're reasonably confident that in O4 we can operate the interferometer at the cryogenic temperature. Next, please. So this is a schedule for O4. Currently, we are finalizing the hardware upgrades, which will continue until the end of the June. And in July, we will close down all the chambers and pump down all the vacuum system. And we will spend 3.5 months for the interferometer commissioning after that. And then do the engineering run, and in December, O4A starts. Now, at the time of the beginning of the O4A, the expected binary range is around 1 megaparsec, which is basically the same as O3GK, because we don't have enough time for the commissioning, so we don't expect too much improvement at that time. And it doesn't make so much sense to continue observing with such a low sensitivity. So after about 1 month, KAGRA will go back to the commissioning mode again, and we will focus on improving the sensitivity. And KAGRA will be back to the observation sometime during O4B with an improved sensitivity. And we plan to have the participation in O4B for about 3 months. Next, please. This is the possible scenarios for the O4 sensitivity. So basically for O4A, as I said, 1 megaparsec is a kind of canonical number for the O4A sensitivity, but because we're replacing the SRM with a transparent one, and also we've been working on the reduction of the technical noise, especially the suspension improvement, we may, if you're lucky, we may be able to go up to 3 megaparsec. And then for O4B, we are planning to do the cryogenic operation, and depending on the level of the technical noise reduction, we're expecting to have somewhere between 10 to 25 megaparsec in O4B. Okay, next slide, please. So this is summary. KAGRA has been conducting the upgrades in the hardware upgrades in various subsystems. And then the plan is to join O4 from the beginning with about 1 megaparsec binary range. But we will leave the observation in the middle to improve the sensitivity, and we'll be back to the observation sometime during the O4B with an improved sensitivity. And I hope to participate in the last 3 months of O4B. That's it from me. Thank you very much.
Thank you so much, Yoichi, and let me thank actually all the speakers. So let me summarize what we discussed today and what we saw. So O4 is planned to start on December 15th on this year. The length is 1 year as it was for O3 with 1 month of commissioning break exactly in the middle of that. We may be able to release alerts during the engineering run before the beginning of the run. That's still been prepared. And there is also a chance that the length of the run might be extended depending on the plans for the O5 upgrades. But of course, if these possibility becomes more concrete, we will signal that well in advance. Concerning the status of the detectors, so we heard from the speakers that activities are ongoing at the sites, all 4 sites, to finalize the installation of the upgrades in view of 4 and to commission the detectors in order to achieve and reach the expected sensitivities for the next science run. As discussed, there are some technical uncertainties there, which are which remain and which, of course, may impact the schedule that is the beginning of the run. In any case, we, as LVK collaborations, will continue to review the schedule and the plans in a quarterly cadence, so that every 3 months we will issue an update. Other than that, as Patrick announced at the beginning of the webinar, we will restart the Open LVK EM meetings in preparation of O4 to update not only on the status of the detectors, but also on the status of the general preparation of the science run from different points of view. And with these, I conclude and I thank again all the speakers and all the panelists and the organization of this webinar and everyone for coming online. And there is still time for some questions if you want. As I said, there is a question and answer button on top of your Zoom bar. I see questions are being asked online, and so I am.
Alessio, perhaps I'll just answer Mandeep's question.
Sure.
About LIGO India Live. So the LIGO India project is progressing. They've made a lot of progress in terms of building their test facility and generating the capabilities in India for it. They've also acquired the land for the observatory. The final funding for the construction of the detector is still awaiting final approval by the Indian government. So that's the current status of LIGO India. Do you want to field Alessio, do you want to sort of field the other questions to people who could answer them live?
Yeah, sure. So there is a question about how long the O4A run will be. Let me take that very, very quickly. That's supposed to be 6 months. And then there is another question from Barak about the an effort to release auxiliary channels of O3. And what is the plan to release data for O4? I think, Patrick, that's for you as well.
Thanks, Alessio. Thanks, Barak. Yeah, first of all, let's talk about auxiliary channels. So there's a release of a small set of auxiliary channels that was already made for O3 around one specific event. The idea behind that was to gauge interest in use of them, and we understand that it's only very limited and therefore can only be used in quite a limited fashion. But we'd still be interested to know what use is made of it, and if people have an interest in seeing the data released for other parts of the run. The long-term goal is from the LVK is that we do have it in our minds that attempting to release at least a subset of auxiliary channels is something we'd like to do, but right now we don't have personnel available to appropriately document all of that. So it's something where we need to understand better the usage models and desires of the community, but we'll be as responsive as we can be subject to funding. The second point a question that Barak asked is the plan to release the data, let me remind people about what our strategy is for the strain data in O4. So our current plan for O4 strain data is that after acquiring 6 months of data, we will wait. Well, wait is not quite right. There will be an 18-month lag before release of that strain data to the public. So the O4A will be released after 18 months after the end of it, and then O4B will be released 18 months after the end of that. Again, the same answer really applies for the auxiliary channels. Our plan is to get there and be able to release those longer term, but at the moment we're still trying to gauge the level of interest from the community and also figure out where we would get the effort to do so.
Thank you so much, Patrick. I see there are other questions coming online. There is another one which I think you might want to take because it is from George Ishman and asking how much extra alert time we can expect for a BNS event with the planet's O5 sensitivity.
Yeah, I think so. George, I don't have a very precise answer to that question right now. A lot still depends on the sensitivities, and in particular the low frequency sensitivities. It also will depend on the signal to noise ratio that we acquire. The typical numbers we carry are that if we got a very loud event and we had good low frequency sensitivity, we could have an early warning alert for a BNS a minute or a couple of minutes before the merger. But that is a very tentative number. We will discuss the details of early warning alerts in our town halls later in the summer and into the fall, so that we have more precise answers to that question for you.
Thanks, Patrick. I think this fact that we will update more in the town halls also applies to the question by Aaron asking whether the scheme of the format of the alerts has been finalized.
Yeah, and again, Aaron, the data I kind of tried to give a little bit of an answer related to that earlier. The details of the changes should be coming out in the early part of the summer, but that's again a tentative date right now. But over the summer, you can anticipate seeing the new format discussed more broadly and examples of using it and other updates that are needed coming into place. Perfect.
Thanks again. I see there is one more question from Kunal about the LIGO India timeline. I don't know if you want to say a few more words about that.
I think on that one right now we don't have any better information from it. project team in India are working as closely as they can with the funding agencies there and with the government to figure out when final approvals will be available. We're all looking forward to having an extra interferometer in India. It will bring great scientific capabilities when it joins the LVK run or network. So that's as much as we really have for you today on that.
Thanks. There is then another question from Mark Luthi about sky localization for BNS early warning.
I think, let me suggest that all of these questions related to the early warning capabilities and the actual capabilities of sky localization are best postponed to the later town hall meetings that will begin in late May or early June. So please bring those questions back to those town halls as we have them.
Perfect. And then there is another question from Norbert. This is directly in the chat, whether the town halls are going to be held face-to-face or not.
Everything right now is for the town halls is intended to be by Zoom. There are a number of workshops going on in other venues where there will be LIGO Virgo KAGRA representatives able to say a little bit about runs. For example, the IAU General Assembly in Busan in Korea will be a venue where there's some discussion of global coordination of multi-messenger astrophysics, but there are other meetings too. So you can anticipate having some small groups of people who can give information at different workshops, but the actual town halls are currently planned to all be on Zoom.
Thank you so much. So I don't see further questions coming up in the question and answer dialog box. And we are then at the end of the hour. So I guess we can thank again everyone for coming online and paying attention to this webinar. Thanks again the speakers and the panelists. And then I think we can close